Hi everyone, in this section we begin our discussion on cardinality, which is essentially about the size of a given set. For a finite set, we can determine its size by counting the number of elements in it. Yet, for an infinite set, it is impossible for us to enumerate all the elements by using only finitely many counting operations. As a result, we have to generalize the concept of the size of a set from finite sets to infinite sets. To get some inspiration, let us first reflect what happens essentially in the process of counting. For instance, we all know that the set of English alphabet has 26 elements in it. This can be easily done by counting the letters A, B, C, D, till X, Y, Z using the numbers 1, 2, 3, 4 until 24, 25, 26. Simple as it is, we should realize that while the English letters are surely just symbols, the Arabic numbers that we have used to count those letters are also a set of symbols. There is no reason to believe that the choice of such symbols will play any specific role in our counting process. Rather, what is important here is the correspondence between each English letter and each unique number we have associated to it. In other words, the process of counting essentially is the process of constructing bijections. Now, once we switch to infinite sets, things immediately become more tricky. As Galileo has already realized in 1638, the attributes equal, greater, and less are not applicable to infinite but only to finite quantities. However, it still makes sense to discuss the possible bijections between the two given sets, even if they are both infinite sets. This motivates the definition of cardinality. Let A and B be two sets. We say that the cardinality of A is the same as that of B if there exists some bijection f from A to B. In this case, we also say that these two sets are equinumerous. We will typically write two vertical bars around the set to indicate its cardinality. Notice that the quantifier here in the statement is the existential quantifier. In other words, to show that the cardinality of A is the same as the cardinality of B, we only need to construct a single bijection. Now let us study some examples. In our first example, we want to show that the cardinality of the natural numbers is the same as the cardinality of positive integers. Let us consider thus the translation map, which sends a natural number n to a positive integer n plus 1. Under this function, 0 is sent to 1, 1 is sent to 2, 2 is sent to 3, and so on. This is clearly a bijection. In other words, the cardinality of the naturals is the same as the cardinality of the positive integers. To see why this result is refreshing, notice that the set of positive integers is a proper subset of the set of natural numbers, where 0 is in the set of naturals, although it is not positive. So we have actually built a bijection between a set and some of its proper subsets. This is clearly not possible for finite sets. Indeed, according to Dedekind, the existence of a bijection between a set and some of its proper subset is precisely the property that characterizes the infinite sets. Perhaps it is easier to illustrate this subtle difference by considering the following scenario, where we have 5 cats, each with its own yarn ball. Now, if another cat arrives, this newcomer will unfortunately has no yarn ball to play with. However, if there are infinitely many cats standing in a row, each with their own yarn ball, then it will be a different story. When the newcomer comes, we can give the yarn ball of the first cat to the newcomer. In return, we can give the yarn ball of the second cat to the first cat. Similarly, we can give the yarn ball of the third cat to the second cat, then the yarn ball of the fourth cat to the third cat. And we can keep going in this way. Since there are infinitely many cats, this process will never terminate. As a consequence, each cat will eventually get a yarn ball after this translation. This is indeed the idea of the Hilbert Hotel paradox, nowadays a popular example that people use to explain the difference between a finite set and an infinite set. Our second example is to prove that the cardinality of the open interval 0, 1 is the same as the cardinality of an arbitrary open interval AB. Again, to prove this, we only need to construct a bijection. To this end, let us consider the affine map F from the open interval 0, 1 to the open interval AB, where fx is equal to b minus a multiplying x plus a. The geometric meaning of this function is fairly straightforward. By multiplying b minus a, we have scaled the original interval 0, 1 of unit length to a new interval whose length is b minus a. This interval is of the same length as that of the interval AB. However, their endpoints still do not match with each other. That is why we then add a to it, which serves as a translation, moving the left end 0 to a and the right end b minus a to b. One can easily show that this affine function is indeed a bijection. Thus, the cardinality of the open interval 0, 1 is the same as the cardinality of the open interval AB. Before we finish this section, notice that we can consider a set A having the same cardinality as that of set B as a binary relation on the class of sets. This relation is reflexive, since for any set A, the identity map sending each x in A to x itself is clearly a bijection from set A to itself. This relation is also symmetric. Indeed, if the cardinality of A is the same as the cardinality of B, this means by definition that there exists a bijection f from A to B. Since f is bijective, it has an inverse which is also bijective. This inverse will then be a bijection from B to A. In other words, the cardinality of B is the same as the cardinality of A, which justifies the symmetry. Last but not least, this relation is also transitive. Given arbitrary sets A, B, and C, where the cardinality of A is equal to the cardinality of B, and the cardinality of B is equal to that of C, we know by definition that there exists some bijection, namely f from A to B, and there exists some bijection, namely g from B to C. From there, their composition will be a bijection from A to C, which means that the cardinality of A is the same as the cardinality of C. Since this relation is reflexive, symmetric, and transitive, we conclude that it is an equivalence relation. As a direct application, let us now consider two arbitrary open intervals. By using the consequence of the previous example, as well as the symmetry and transitivity, we see that any two open intervals are of the same cardinality.